Arid landscapes are defined by an extreme deficit of moisture and the unrelenting force of prevailing winds. To capture the rare rainfall that does occur, traditional civil engineering relies on the Liman, a rigid, bulldozed basin designed to trap runoff so vegetation can take root. Constructing these basins requires heavy earth-moving machinery, diesel fuel, and high capital expenditure in remote areas where supply chains barely exist. When a seasonal flash flood finally arrives, the sheer hydraulic force of the water routinely overwhelms and erodes the static earth berms. Rigid human infrastructure fails in the desert because it treats chaotic wind and water energy as adversaries to be blocked, rather than dynamic forces to be managed. The alternative requires infrastructure that treats aeolian transport and flash floods as construction partners. Nature routinely carves out functional moisture traps without any heavy machinery. Specific aerodynamic depressions slow down wind and water, creating localized reservoirs where tall vegetation can actually thrive. Replicating this phenomenon systematically is the basis for a protocol known as the self-forming Dune Liman. We can deploy lightweight, programmable modules into a degraded landscape to physically coerce the wind and water into printing a water-capturing geometry automatically. Instead of degrading with every storm, this dynamic sand architecture constantly catches new material, repairing its own slopes and reinforcing its structural footprint. We are taking the raw physics of geomorphology and turning them into programmable software. To map the precise slopes required for a stable sand architecture on Earth, we look to the extreme physics of Martian dune fields. Experiments replicating Mars observed a distinct regime change. When solid blocks of dry ice interact with slopes below 22.5 degrees, they safely burrow channels. But hit 25 degrees, and the blocks begin an uncontrolled, damaging slide. We translate those planetary mechanics directly into strict geometric boundaries for our Earth-based design. The windward ramp, known as the stoss, is held at an exceptionally shallow angle of just 2 to 5 degrees, maximizing water infiltration and allowing wind to push new material upward. The leeward face is aggressively constrained, engineered to remain completely stable under 15 degrees. Dry sand naturally piles up to its angle of repose, between 28 and 34 degrees. We treat that range as an absolute failure zone, where gravity overpowers friction, initiating an avalanche. By strictly enforcing sub-repose angles across the entire structure, the resulting earthwork easily absorbs the shear stress of Earth's storm force gusts without collapsing. The hardware module used to enforce these exact angles consists of a 4-meter UV-stabilized mesh fence attached to a motorized servo. Local wind vane sensors actively monitor velocity. Once they record a sustained breeze above 2.5 meters per second, the print cycle activates. The motorized servos immediately rotate the mesh fences into the path of the incoming air, forming a physical barrier against the flow. This top-down diagram shows how locking the fence at an exact 60-degree angle creates a deliberate wind shadow. The air pressure drops in the wake of the mesh, forcing the gust to deposit its payload of suspended sand particles. The accretion process begins. Sand aggregates at the base of the fence line, slowly building the ramp upward. Localized LiDAR sensors monitor this growth. When the base accretion hits 0.4 meters high, the system must adapt to prevent exceeding our safety parameters. The servo physically lowers the fence angle to 30 degrees. This alters the aerodynamic flow, pushing the deposition footprint outward to extend the shallow 2 to 5 degree stoss slope. To handle flash floods, inflatable bladder dams embedded in the ground automatically deploy, adding immediate water retention to the dry wadi. Operating on a continuous 10-minute loop, the array seamlessly toggles between harvesting airborne sand grains and capturing seasonal floodwater. Relying on a single chain dune carries immense risk. If a severe lateral storm hits, an isolated sand wall will scour and wash out. We mitigate this by adapting a principle from the restoration of Geneva's air river, which replaced hard single-channel banks with a self-adjusting braided corridor. This schematic maps the hybrid fan plus nodes architecture, applying the braided river concept to a 1-hectare desert installation. The outer component is a wide, horseshoe-shaped sand rim. When sudden floodwater arrives, this rim breaks the initial momentum, spreading the incoming sheet 360 degrees. Inside the rim, we print 16 diamond-shaped islands. These mounds are built on PLA frames and stabilized with an active mat of honeycomb mycelium. The incoming sheet flood naturally fractures, separating into a network of small, slow-moving streams that weave easily around the diamond structures. This braided topography distributes hydrodynamic turbulence evenly across the entire footprint, protecting the main ramp from concentrated erosion. The channels soak up moisture, establishing staggered wet pockets and dry zones that support distinct microclimates and diverse crop zoning. Eliminating any single point of failure ensures the entire hectare remains intact, even under the assault of a violent desert downpour. The layout of those diamond islands defines a specific grid of 1-meter-wide interior trenches. As nocturnal breezes pass through these narrow gaps, the air must accelerate, creating a sharp drop in pressure known as the Venturi effect. This diagram shows the iron oxide meshes spanning the trenches. The Venturi-driven pressure drop rapidly cools the local air, forcing atmospheric moisture to condense directly onto the fibers. This creates localized optical rain, passively pulling the equivalent of 20 to 30 millimeters of water per year out of dry night air. Over months of variable winds, even the most carefully designed sand geometry will begin to deform and drift. To prevent collapse, the network relies on an artificial intelligence model known as the Force-from-Image Convolutional Neural Network. After a storm, a drone scans the Liman. The video is fed into the Edge GPU, which generates a high-resolution analysis of the entire surface. The AI maps the resultant force on individual sand grains, detecting microscopic shear stress to locate high sliding risk areas before they slump. Once a hazard is identified, the network outputs new rotational coordinates, angling the pivot fences to catch fresh sand and reinforce the weakened sector. The AI acts as an autonomous groundskeeper, continually adjusting the hardware so the fluid dynamics never breach the strict constraints derived from Martian geology. Deploying a single hectare captures localized water, but linking hundreds of these nodes together along the aridity front creates a macro-level barrier. This forms a breakbelt, a 300-meter-wide, self-forming topographical shield that physically dissipates hot storm winds and traps migrating sediment. Lowering wind velocity and cooling the soil creates a massive climate buffer, establishing the precise conditions needed for lush orchards to take root directly downwind. Yet large-scale ecological restoration is entirely dependent on economics. A global deployment requires a competitive return on investment. The Dune Liman generates direct revenue through co-products, the finest silica sand aggregates at the dune crests. We harvest this material and fuse it in solar furnaces to cast high-value sun-glass tiles, engineered specifically for greenhouse glazing. Second, we embed pocket reverse electrodialysis cells into the damp soil. These red units exploit the natural chemical differences in ground salinity to generate electrical wattage. This salinity gradient produces enough continuous power to run the AI sensors and mechanical servos indefinitely, operating fully off-grid. We can halt desertification by abandoning static earthworks. By deploying programmable, revenue-generating hardware, we can leverage wind and water to turn sand into a self-assembling architecture.